Hello, yes, can you hear me?
Yes, sir.
Okay, so we will wait for a few minutes more. Let others join, and then we will start at 7:10.
Okay, sir.
So, hello everyone, a very good evening to all. So, I once again welcome you all for this second interaction session on the course Atomic and Molecular Physics, which is being flowed this session in January 2025 with course code NOC24 PH04. I hope my voice is clear to everyone.
Yes, sir,
Yes, sir.
it's clear.
Okay, so uh, um, in the first interaction session, we discussed about the uh, uh, some of the problems that were covered in the course content of week one. So today we will discuss a few problems that will be based on the lectures of week two. So myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, Plasma Physics Laboratory, IIT Delhi. So once again, so in order to join in this interaction session, so this is the meeting link. However, if you are not being able to join through the meeting link, then you can join through the meeting ID and the password. A meeting ID and the password is given here. And generally, I take sessions on each Monday from 7 p.m. to 9 p.m. And it will continue till I complete the 12 lectures or 12 sessions. And for the recordings of the interaction sessions that we are conducting every Monday, you can visit my YouTube channel where the videos are being uploaded after each interaction session, the next day of the session. Then for the presentation slides that I discuss problems, you can refer to the Google Drive folder and the link is provided in this page. I will also from NPTEL side, you must be getting the links and the meeting link as well as the link for the Google Drive folder, I guess. Then discussing about the concepts that were covered in this week's lecture. So in this week lectures, basically the lecture from 6 to 10, concept related to the structure of atom was covered, which in which it was discussed about Thomson's model, other force model, and Bohr's atomic model. And during the discussion of the structure of atom, then discussions were also done related to the blackbody radiation curve. Then the corresponding discussion for hydrogen atom spectra and X-ray spectra are also conducted. So we will be solving a few problems that will be based on this concept today. So let's start our discussion. And before starting any discussion, if anyone has any doubt from the previous session also or any doubt, you can ask me. You are free to ask. Okay, so we will start solving the questions. So question number one, the question says the energy needed to ionize a hydrogen atom in its fast excited state is option A minus 13.6 electron volt, option B plus 13.6 electron volt, option C 27.2 electron volt, and option D all of the above options are wrong. So the question says what is the energy needed to ionize a hydrogen atom in its fast excited state?
13.6.
Sorry, the answer is
Sir, did you say first excited state?
yes. Can't you see the screen?
No, sir.
Is my screen is not visible to you?
No, sir, not visible.
Okay, 1 minute. I think I am sharing my screen. You can't see my screen.
Sir, it's showing
Yes,
white.
sir, it's visible.
Sorry.
Yes, sir, visible.
So can you see my screen or not? Wait a minute. My voice is clear,
Yes, sir.
but you
Yes,
can't
sir.
see my screen.
Sir, in my screen, it's showing white.
Any other who is facing the same problem?
No, sir, it's visible.
Okay, so I think so. Who can see? I think yes, you can't see my screen.
Yes, sir.
Okay, so I think you have some network issues in your end, I guess, because All others
Okay.
are being able to see my screen. So, but however, let me stop presenting it and then share it once again. Wait a minute.
Okay, sir.
So, can you all now see my screen? So yes, can you now see?
Sir, I think there must be some issue with my network connectivity.
Okay, maybe because since all others are being able to see it. So now the question says the energy needed to ionize a hydrogen atom in its fast excited state, and options are option A minus 13.6 electron volt, option B plus 13.6 electron volt, option C minus 27.2 electron volt, and option D all of the above options are wrong. So I'll give you a few minutes to think about this question, and kindly note that the question says the hydrogen atom is in its fast excited state. So that keep that in mind, and then we will discuss after a few minutes.
Sir, option B.
Sir, option D.
Sir, option D.
So can anyone tell me what will be the correct option?
Sir, option D.
Option
Sir, option
Okay,
D.
so why option D? मतलब why not minus 13.6 electron volt or plus 13.6? Sorry, I mean what will be the correct answer then? not about the option I am talking.
The
That will be
3.4
the
electron volt.
minus 3.4 electron volt.
okay, it will be plus 3.4 or minus 3.4.
Minus.
Yes. Can you tell me what will whether it will be minus 3.4 electron volt or it will be plus 3.4 electron volt?
So minus 3.4.
Minus.
Are you sure? So no, actually it will be plus 3.4 electron volt. So let's discuss. So we know actually this question is based on Bohr's model because the model that the very fast model which basically comprehensively discussed about a few properties of atom, that was more or less the Bohr's model, because all other models they were able to discuss a few things about the atom. However, there were no quantifications like what will be the orbit, how will be the radius of the orbit calculated, and all these things. So, for example, in Rutherford's atomic model, he told that electrons are revolving around the nucleus in certain orbits, but Rutherford did not give any explanations and all. But Bohr, when he gave his model for basically hydrogen atom or single electron atom, and he then discussed about a few things, and this question is based on the concept of Bohr's model for hydrogen atom. So now if we talk about the Bohr's model of hydrogen atom, so let's discuss briefly about that model. So according to Bohr's atomic model, uh, so he gave a model in which he said we know the nucleus is present at the center, and nucleus contains positive charge, and almost all mass of the atom is concentrated at the nucleus. So in nucleus there are mainly protons and neutrons. So if you talk about the charge, since neutrons does not contribute towards the charge, then the total charge will be plus JD. So as I talked a few minutes before, Bohr gave the model only for hydrogen atoms and hydrogen like atoms. So for hydrogen like atoms, here we are lighting JD. So hydrogen like means hydrogen like atoms. That means atoms who have atoms who have one electron only. So H atom, then helium plus, helium has two electrons. So
Yes,
it
sir.
helium, we are taking helium plus atom, then helium plus atom will be having only one electron, because it has given its one electron, that's why it is helium plus. Then lithium 2 plus. So basically this model that Bohr gave, it is mainly valid for these uh, hydrogen like atom. So if you talk about a few postulates, so what Bohr said that since the electrons are revolving around the nucleus in certain circular orbits, so first thing you should notice that he said that the orbits are circular, but actually after if you discuss after in the next upcoming lectures, you will know Sommerfeld modified this, and he said that there are not only circular orbits, there are elliptical orbits also. So, but according to Bohr, the orbits are circular in shape. So he said that since it is a circular motion of electron around the nucleus, so we know for circular motion we need a force which is called as centripetal force or centrifugal force, and then this force is getting balanced by the Coulombic interaction force between the nucleus and the electrons, because electron is negatively charged. Suppose this is one orbit and this is electron. So its electron is negatively charged and the nucleus is positive charged. Since and also the range of the Coulombic interaction is infinity, because only at infinity there will be zero force. Otherwise, whether it is 1 meter or 1000 meter, there will be some force between the two charged particles. So since the electron is revolving around the nucleus, so there is a force of Coulombic interaction, or basically Coulombic attraction between the nucleus and the electron, and that force provides the necessary centrifugal force for revolving, for the electron to revolving around the nucleus. So if you can say, so according to we know the centrifugal force, the expression is mv square by r, and now if you compare it to the Coulombic force of interaction, so it will be k z e square by r square. So this was the one of the postulates of Bohr. So this is one equation, and then also Bohr said that electron can revolve in only those orbits where the angular momentum electron is quantized. This basically the angular momentum of electron is an integral multiple of h cross. So another, we know angular momentum uh, is mvr, which is integral multiple of h cross, that is n h cross or nh by 2 pi. So these were two main one of the two main two of the most important postulates or concept related to the Bohr's model of atom. And then by using these relationships or dependence of the two forces, the balancing of the two forces, then Bohr was able to derive the expression for the radius of nth orbit. Suppose this orbit is nth orbit, n can be any value where n starts from 1 and then goes up to higher values with increasing 1, 2, 3, 4, like that. So he gave the expression for Rn, that is the radius of nth orbit, then Vn, the velocity of the electron at the nth orbit, and the energy of electron at the nth orbit when it is revolving. Because according to Bohr, as long as the electron is revolving in an orbit or stationary state, so why it is called, otherwise called as stationary state? Because the energy of that orbit remains stationary. There will be no change in its energy. So this En is constant for a particular state, and that particular state means for a particular value of n. With so these as the expression we will now let's see the expressions. So according to Bohr, so what will be the expression for Rn? Rn will be n square h square epsilon 0 by pi m z e square, where n is the orbits, then h we know Planck's constant. Can anyone tell me what will be the value of Planck's constant? Yes,
6.62 into 10 to the power minus 34.
unit.
So joule per second.
Once again,
Uh,
joule into second, not plus.
Oh yes, sir. Joule second.
So joule into second. If you are writing 10 to the minus 27, then it will be arg into second. So then here m is the mass of electron, and z is the atomic number, and epsilon 0 we know epsilon 0 is permittivity of free space, which is 8.85 into 10 to the power minus 12. That is the unit. Yes. What will the unit of epsilon 0?
Uh,
Coulomb square per
Coulomb.
Newton meter.
Newton, sorry, Coulomb, sorry, it will be inverse of that.
Coulomb
Yes,
Because
sir.
square per Newton meter square.
exactly, because the it is F is equals to 1 by 4 pi epsilon 0 q1 q2 by r square, and 1 by 4 pi epsilon 0 becomes 9 into 10 to the power 9 Newton into meter square per coulomb square. So now you can see here Rn is direct proportional to n square, and it is inversely proportional to z. Similarly, if you talk about velocity, the expression for velocity is z square by 2 epsilon 0 nh. And if we talk about the energy, the expression for energy of nth orbit is En equal to minus 1 by 8 n square h square epsilon 0, sorry, it will be m z square e fourth by n square h square epsilon 0 square. So from here you can say, so you can clearly see, if you talk about the energy, then En is directly proportional to z square, and it is inversely proportional to n square. And if you put all these values here, you will get En equals to minus 13.6 Z square by N square electron volt. So why the question comes, why this is negative? We know the negative sign implies that the force of interaction that is between the electron and the nucleus, it is attractive in nature, because in order to overcome that force, you need to provide energy, and that energy is positive. That's why, so if you want to remove an electron, or if you want to excite an electron from one state to another state, you have to provide energy, and if you are providing energy, so you are giving it positive value of energy, that is you are mm, basically supplying to that electron, and then the electron will absorb that energy, and then after getting, so it will depend upon how the electron will transition occur, how the transition will occur, it will depend upon the energy value you are supplying and the energy value electron is present in that state. So if you talk about the question, then the question was, what is the energy needed to ionize a hydrogen atom in its fast excited state? So if you are talking about hydrogen atom, so we are talking about hydrogen atom, then for hydrogen atom Z is equals to 1, and for fast excited state, so n equal to 1 is for which state? Yes,
A ground
what
state.
will be the, exactly, so for ground state n is equals to 1, then but the question says it is fast excited state, so for fast excited state n will be 2, fast excited state. So if you talk about the energy of the electron in the fast excited state, so the energy of the electron in the fast excited will be, in case of hydrogen atom, it will be minus 13.6 into 1 square divided by 2 square. Okay, minus 13.6 divided by 4 is minus 3.4 electron volt. Now see, this energy corresponds to the energy of the electron, but the question says the energy needed to ionize a hydrogen atom in its fast excited state. So what is the so can anyone tell me what is called as ionization energy?
The amount of energy required to remove an electron from its shell.
Sorry, in 1 minute, let me write ionization energy. Yes. So ionization means the electron will, there will be a transition of electron from one state to another state, isn't it?
Yes,
So
sir.
now tell me what we are saying, what you are saying.
So the amount of energy required to transition of an electron from its current state to an infinity state, n equals to
Exactly.
infinity.
So it basically it means if you are ionizing an electron, so you are removing the electron from that atom to a distance where there will be no effect or no influence of that nucleus or of that atom. So as I just mentioned, as long as your distance is finite, there will be interaction between the nucleus and the electron. But if you want to ionize the atom, you need to make the atom free from a particular electron. So free means, so you need to free the electron. Suppose this is an atom and the electron is revolving here, and this is plus Jd, and suppose this is a distance Rn, and then you need to, if so you need to ionize that atom, means you need to remove an electron so that there will be no influence of the nuclear force or the force of that nucleus on that electron. So here will be Rn will be infinity. So for infinity means we can say, if you put here, now you say, you see 1 minute. Also the value of n will be infinity, because since Rn will be infinity, then n will be also infinity. So from n equals to 2 to n equals to infinity, is not it? This is called as ionization from fast excited state. So if you want to ionize an hydrogen atom in its fast excited state, so we need to remove that electron which is currently revolving at an state of n equal to 2 to infinity, that is n equals to infinity. So now if you talk about the expression for energy, it will be minus 13.6 z square by n square in general. For hydrogen atom, it will be minus 13.6 by n square. So initial, so what will be the ionization energy? Ionization energy means ionization energy is final energy minus initial energy. So initially it was at n equal to 2 state. Now it is present at n equal to infinity state. So we know for infinity, if you put value n equal to infinity here, it will give you 0. So E final is 0. So what is the energy of ionization? It is 0 minus of minus 3.4 electron volt, which is 0 plus 3.4 electron volt. Then it will give you 3.4 electron volt, which is positive, because you are giving external energy to that electron. So in order to ionize the electron from hydrogen atom to fast excited state, you need to provide plus 3.4 electron volt energy. So all these options are not correct, because so the correct option will be option D, that is all of the above options are wrong, and the correct answer will be 3.4 electron volt. Now it is clear to everyone why it will be plus and it will not be minus.
Yes, sir.
Okay, so again another thing. Yes, someone was saying something. Okay, so we'll now one more thing. So here you see another important postulates of Bohr's model was electron can revolve in certain stationary states or orbit. However, electron can be present in between two orbits. So either it will be n equal to 1, and n equal to 2. So electron can't move in between n equal to 1 and 2. So the energy of the electron is quantized. So as long as electron is present in an atom, it will be either present in, so suppose an electron is present in an atom, so there will be n will be either 1, or n will be either 2 or 3 or 4, like that. So since n has discrete values, so the energy of the electrons are also discrete. So if you talk about the energy levels, then n equal to 1 will be, this will be n equal to 1, then n equal to 2, then n equal to 3, then n equal to 4, like that. So this is minus 13.6. And you see one thing you should understand, the difference between the, or the difference between the energy of the two adjacent orbits are not same, because if you talk about the expression, it is inversely proportional to n square. So the first orbit is minus 13.6, the next orbit is minus 3.4. So here there is an energy difference of 10.2 electron volt, but for next orbit this will be smaller and smaller. So as you go on increasing the value of n, then the orbits will become closer and closer, and then there will be, after sufficiently high value of n, then there will be a continuous energy band. But as long as the electron is present inside the atom and close to the atom, its energy is discrete and it can't attain any value of energy. So if you want to ionize the electron, you need to supply certain amount of energy, only then electron will get out of the atom and then your atom will be ionized. So now we'll move to the next question, question number 2. So one more thing, let me, so you can all see my screen.
Yes, sir.
So
Yes, sir.
so as I can see, there are 4 students here. So first I will start from yours. So yours, you can you introduce yourself? Where are you from, or in what course you are currently enrolled? Like
Yes, sir. Good evening, everybody. I'm Yash Srivastava. I'm currently in Hindu College, University of Delhi. Currently pursuing my bachelor's in physics honors, and I am in second year right now.
Okay, so BSc, you are in BSc second year. Okay, so then next, Sulochana, can you hear me?
Good evening, sir.
Yes.
I am
So
Sulochana. I currently I am reading in MSc Physics in second year at Sambalpur University.
Sambalpur University.
Yes, sir.
Okay. So next, Pragyan Tripathi, you are from, so Sulochana, you are studying in MSc second year.
Yes, sir.
Okay. Then Pragyan Tripathi, you. Yes. So can you introduce yourself, Pragya? So at least you can you tell whether you are studying in BSc or in MSc? Because want to know the courses you are in, so that I will try to explain it accordingly. Yes. Your voice is not clear. Sorry. Okay. So I think there is some issue with your mic, I guess. So let's continue our discussion. However, I so we can talk about it later. So let's continue our discussion now. So now we will go to question number 2. The question says the fast line of Balmer series, that is from n equal to 3 to n equal to 2, is 656.5 nanometer. What is the wavelength of fast line of Paschen series, where the fast line of Paschen series corresponds to the transition from n equal to 4 to n equal to 3? And the options are: option A 1313 nanometer, option B 328.25 nanometer, option C 1875.7 nanometers, and option D 164.125 nanometers. So these are the four options. The question says the fast line of Balmer series, the fast line of Balmer series, the wavelength is 656.5 nanometer. Then what will be the wavelength of fast line of Paschen series? So I'll give you a few minutes to think about this question and try to solve it, and then we will discuss what will be the correct answer.
For option C.
Yes, so correct option will be option C, that is
Okay.
1875.7 nanometer. Yes, so how we will solve it?
Sir, by using Balmer series formula.
Okay, so first let's discuss about the expression for the wavelength when there is a transition occurring between the two energy levels. So now if you see, there was the expression for energy, which was inversely proportional to n square. So now if we talk about the transition from nf to n, suppose here for the given case, suppose question said it is Balmer series. So suppose this is Ni is the, suppose, let me 1 minute. So suppose this is NF means final state, and that Ni means it is in initial state, or you can name it as N1 and N2. So here you see the transition is occurring from n is equals to 3 to n equals to 2. So so 1 minute. So we can change the. So if you talk about the expressions, so the expression for wavelength, if there is a transition occurring between two states, so the expression is 1 by lambda is equals to r 1 by ni square minus 1 by nf square. So here for Balmer series, if you talk about Balmer series, so what will be ni and what will be nf?
And I will be 3 and 2 will be 4.
So it 1 minute. Can you say that again?
Ni is
And
the
I
3 and N2 is the 4.
No, for Balmer series. So can you tell me uh, when Balmer series basically appear or Balmer series is emitted? So as I discussed, so there are different energy levels in a hydrogen atom. Suppose this is n equal to 5. So when an electron absorbs some amount of energy or emits some amount of energy, it will get transited to higher or lower orbit. So since the energy at the ground state is lower, so when an electron absorbs energy, it goes from lower to higher orbits. So when an electron absorbs energy, it will go from lower to higher orbit, and when an electron emits energy, it will move from higher orbit to lower orbit. So this is when an electron emits energy. And when we are talking about this series, Balmer series, so there are different series in hydrogen spectra. So if you talk about spectra, there are two types of spectra. One is absorption spectra, another is emission spectra. So here we are talking about which spectra, absorption or emission? Yes. Can anyone tell me?
sir, can you repeat the question?
So here we are talking about Balmer series, Paschen series. So these are the series, they corresponds to hydrogen spectra, is not it?
Yes, sir.
Whether they are hydrogen emission spectra or they are hydrogen absorption spectra.
Uh,
These series corresponds to, or these series are present in hydrogen emission spectra, because these wavelengths are getting emitted, they are not getting absorbed. So when you see, can anyone is there anyone who has seen hydrogen spectra or hydrogen discharge?
sir, like I am currently having experiment in my modern physics in which I have to like find H alpha and H beta. So in that,
You have to,
so
sorry.
find the like wavelength of H alpha, H beta, H gamma, like that, and
Exactly.
then
So
calculate Rydberg constant. So over there, I have seen the spectral lines.
exactly. So these spectra are emission spectra. These are not absorption spectra. So in emission spectra, it corresponds to the difference between the energies that the electrons are emitting. Now you are clear. So these spectra, since these are emission spectra, or these are the series, these are different series that are appearing in the emission spectra. So basically these spectral lines or these wavelengths come from the transition of electron from higher to lower orbits. Basically I was trying to tell you that. So since there are two type of transitions, one is absorption transition, another is emission transition. So since you are seeing the radiation, so the electron is emitting the radiation. So the electron is emitting the radiation means the transition is occurring from higher n orbits to lower n orbits. So since if you are talking about Ni and Nf, so here Ni will be the minimum orbit or the lower n value orbit, and Nf will be maximum. So if you talk about Balmer series, Ni will be 2 and Nf will be 3, 4, 5, 6 like that. Similarly for Lyman series,
Ni will be 1 and Nf will
1,
be 2, 3
Nf
to
will be
infinity.
2, 3, 4 like that. So that's why I just omitted that Ni and Nf because it might be confusing. But you can say, you can just write, you can write it 1 by n1 square minus 1 by n2 square also, where n1 will be smaller and n2
Ni.
will be larger, because the wavelength can't be negative or the frequency also can be negative. So this term needs to be higher. So it will be higher only when your in this value or the denominator, suppose this is n1 and n2, then for 1 by lambda to be positive, n1 should be less than n2. So for here ni should be greater than ni should be less than nf, and for correspond to different transitions or different values of ni, there are different series named. So Lyman, Balmer, Paschen like that. So here the expression for uh, wavelength of radiation when the electron gets transited from one orbit to another orbit is 1 by lambda equal to r 1 by ni square minus 1 by ns square. So now the question says the first line of Balmer series. So let me draw the Balmer series. This is n equal to 2. We are not drawing n equal to 1. So n equal to 2, then n equal to 3, n equal to 4, n equal to 5, then n equals to infinity. So if you talk about the transition, there will be 1, 2. So this is one series. This is
Lyman series. Ah, sir, Balmer series.
n equal to 2. So this is Balmer series. Then for n equal to 3, this will be 1, 2, 3 like that. So this will be
Paschen.
Paschen series. So H alpha, H beta, you are just saying, na, I think you said he is going to measure the H alpha, the wavelengths of H alpha, H beta, and H gamma. So H alpha, H beta, H gamma, they corresponds to which series? Lyman series or Balmer series or Paschen series?
Balmer series, sir.
Exactly. So they correspond to Balmer series because
Visible spectra.
Balmer series lies in the visible region, that is between 200 to 2000. Sorry, it is not 200, 200 to 1100, I think, the visible range.
Sir,
So
it was around 600 nanometers, right?
yes,
700 nanometers.
H alpha comes around 656 nanometer, I guess, and then
Yes,
H
sir.
beta 436 or like that. So nanometer. So this so Balmer series. So the transition that occurs from n equal to 3 to n equal to 2, it is called as H
H
alpha.
alpha.
Then n equal to 4 to n equal to 2 called H beta. N equal to 5 to n equal to 2 H gamma, like that. So here the question says the first line of Balmer series. So your first line means n equal to 3 to n equal to 2. So if you put that in the formula, then we know 1 by lambda is equals to r 1 by n1 square minus 1 by n2 square. So for Balmer series, 1 by lambda will be r 1 by 2 square minus 1 by 3 square. So it will be how much? R will be 36.
5 upon 36.
9 minus 4, so it will be 5R divided by 36. So 1 by lambda will be 5R divided by 36. So R will be how much? Because here only one unknown is R, because we know the value of lambda. So what will be the value of R? R will be
1.097 into 10 raised to the power 7.
36 36 by 5 lambda. So actually here we don't need to uh, basically take the expression for r, and we don't need to put the individual values of the expression, because here r contains some quantities like mass of the electron, charge of the electron, and Planck's constant, all these things. Because you can see here, since n square and z square are taking out, so if you see these values and this m and minus 1 by 8, they basically correspond to the constant r. Here r is called as the Rydberg's constant. So here, since the value of lambda is given here, so we can calculate the value of r. But however, we if you so next we should calculate the second part. What is the wavelength of the first line, that is n equal to 4 to n equal to 3. So for past chain series, the value of lambda, suppose this is past chain, then it will be r 1 by n1 square minus 1 by n2 square. It will be r 1 by, this is 1 n is equal to 4 to n equal to 3, so it is 1 by 3 square minus 1 by 4 square. So 1 by 3 square minus 1 by 4 square. So it will be r 1 by 9 minus 1 by 16. So it will be 16 minus 9 r divided by 16 into 9. So it will be 7r by 16 into 9. So we know the value of r, it is 36 by 5 lambda. So lambda past chain will be how much? It will be 16 into 9 divided by 7r, which is 16 into 9 divided by 7 into r is 36 by 5 lambda. So it will be 5 lambda by 36. 5 lambda by 36. Then 9, 4, 4. So it will be 20 by 7 lambda. So 20 by 7 into lambda was given to us 656.5 nanometer. It will be into 656.5, which will give us 1875.5 nanometers. So the correct option will be, so this is the correct answer, and the correct option will be option C. So is this clear to everyone? So also,
Yes, sir.
sometimes, so now it is given, it is first line of armor series or first, then we need to calculate the past tense series. However, sometimes question comes like, what will be the wavelength of, what will be the maximum wavelength corresponding to Balmer series, what will be the maximum wavelength, or what will be the minimum wavelength corresponding to Balmer series. So can anyone tell me what will be the max, so which transition will correspond to the maximum wavelength in Balmer series? Here can anyone
From
tell me?
Sir,
infinity to 2.
just a second. No, sir, with second and third. Maximum wavelength is between adjacent maximum wavelength, because E is equal to h nu equal to hc by lambda. So maximum
Exactly, that's
wavelength we
why,
have to,
exactly. So you
for
here you can
maximum
see here,
energy we have.
you can here you can clearly, so there is another way to understand it. Basically, energy difference is getting emitted, so the wavelength of light that is getting emitted will correspond to the energy difference between the two states. Now if you talk about the energy difference between n equal to 2 and n equal to 3 is how much? It is 3.4 electron volt, sorry, not 3.4, so it is 3.4, and it is uh, what will be the,
13.6.
no, n equal to 2 here, there is no n equal to 1 here. 13.6 divided by 9 will be the n equal to 3 states energy.
Sir, 1.5.
So it is 1.5. Yes. So it is 1 minute. So this is 3 point minus 3.4. This is minus 1.5. So there is some gap around 1.9 electron volt. But if you talk about this energy gap, that is n equal to infinity and n equal to 2, then we know n equal to infinity means 0 electron volt. So the gap between the two will be how much?
3.4.
And we know E is equals to h nu or hc by lambda. So when the energy between the two level is more, the wavelength will be less. So for n equal to infinity to n equal to 2, since the energy is more, the wavelength will be lesser, corresponding to n equal to 3 to n equal to 2. So the maximum wavelength in Balmer series corresponds to n equal to 3 to n equal to 2, and the minimum wavelength corresponds to n equal to infinity to n equal to 2. Is this clear to everyone?
Yes, sir, it is clear.
So for H alpha we are getting 656, but for H beta it is 400 something. So with increase in the value of NF, we will get lesser wavelength because the energy difference is getting bigger and bigger. So this is the one type of question: what is the maximum wavelength corresponding to Balmer series or minimum wavelength corresponding to Balmer series? So first line corresponds to maximum wavelength and last line corresponds to maximum frequency because the energy difference is more. So here, so I hope this is clear to everyone. So this type of question, otherwise it will this otherwise so the question can be framed otherwise, like what will be the maximum wavelength, what will the minimum wavelength, like that. So let's talk about question number 3. The question number 3 says the emission spectra series of hydrogen atom is shown in figure below. What is the series name marked as Z? So here I don't.
Question.
So let
Sir, I
me.
think it is line 1 because it is coming to 1.
So let me write it because I don't think everyone will be able to see the values of n. So n equal to 1, x is n equal to 1, n equal to 2, y, n equal to 3 is z. So can anyone tell me now what will be the
Partial series.
Bastian series, sir, because n is 3.
exactly? So here z is Bastian series. So what will be y?
Balmer.
Y will be Balmer series. Then x will be
Lyman.
Lyman series.
Lyman series. So Balmer series corresponds to visible range. So can anyone tell me uh, if you are talking about Bastian series or Lyman series, then suppose Balmer series has wavelength lambda, or the first member of Balmer series has wavelength lambda, and the first member of Lyman series has wavelength lambda 2. Suppose this is lambda 1 and this is lambda 2. So what is the relationship between lambda 1 and lambda 2?
Lambda 2 is less than lambda 1.
Yes, because the energy difference is more. From n equal to 2 to n equal to 1, the energy difference is more, so the wavelength will be lesser. So a lambda 1 will be greater than lambda 2. So since the energy difference is more, the Lyman series corresponds to ultraviolet region,
Ultraviolet.
and the Bastian series similarly for
Infrared.
Bastian series it will be lambda 3, and lambda 3 will be greater than
Lambda 1.
lambda 3 will be
Lambda.
less than lambda 2, and it will corresponds to infrared region. So this X series corresponds to ultraviolet region, this corresponds to visible region, and this corresponds to infrared region. Then there will be near infrared, far infrared, like that. So
Lambda 3 will be greater than lambda 2.
exactly. Sorry, yes, this
Written
is
less
the
than.
Balmer is lambda 1. Okay, sorry. Correct. So lambda 3 will be greater than lambda because the energy. So the energy difference between the two energy levels is getting emitted. So when you are giving external energy, it will be absorbing the energy and it will emit from, it will get transition from lower orbit to higher orbit. However, when the transition occurs from higher orbit to lower orbit, then the difference between the energy gets emitted, and that radiation we see, and this is called as emission spectra. And in case of absorption spectra, generally in emission spectra we see there are different lights. Like if you talk about emission spectras, so we see there are series of lines. Suppose there are one series here, one series here, like that. So we will see these, and other will we can't see other portions. But in case of absorption spectra, it is completely opposite. So first if we will send a light, then after getting absorbed, some portion of the light we can't see. We will see the other lights, and some we can't see, because that in corresponding to that wavelength, the energy is getting absorbed by the electron and it is getting transited from lower orbit to higher orbit. So these lines we are seeing corresponds to emission spectra. However, for absorption spectra, the line won't be seen. We will see the remaining part of the uh, line or light we are incidentating, but the part that got absorbed by the electron we will not see, and we will get a black line at that point. So this is the basic difference between emission spectra and absorption spectra. So now we'll move to the question number 4. Question number 4 says, compute the wavelength of the H beta spectral line, that is the second line of Balmer series predicted by Bohr's model. The H beta line is emitted in the transition from Ni equals to 4 to Nf equals to 2. So here the formula that I wrote in the previous question, the formula will be changed, because here Ni is 4 and Nf is equals to 2. So what will be the expression for 1 by lambda? So this will be Ni or Nf? The first N. This will be Nf and this will be Ni. Because here Ni is 4 and Nf is 2. And the value of R is given. R is 1.097 into 10 to the power 7 meter inverse. And the options are option A 345 nanometer, option B 486 nanometer, option C 539 nanometer, option D 602 nanometer.
Option B, sir.
Sir, option B.
So the correct option will be, once
Sir,
again,
option B. Option B.
yes, this is 486 nanometer. So it will be pretty much similar to the previous question or the second question we discussed. So if you talk about the expression, this is the expression. Here it will be 1 by Nf square minus 1 by Ni square. However, if you are, so since we are talking here, we are talking about the Balmer series and other series, and these are corresponding to emission spectra. So the expression is 1 by Nf square minus 1 by Ni square, where Nf is less than Ni. But if I will talk about the absorption series, then it will be 1 by lambda is equals to R 1 by Ni square minus 1 by Nf square, where Nf is less than Ni. Here Ni will come in place of Nf and Nf will come in place of Ni. Is it clear now?
Yes, sir.
Yes, sir, it is. It is
Exactly.
obvious, sir, because energy can't be negative.
Exactly. So in order to make whether it is energy can be negative. Energy can be negative.
Yes, sir, potential energy is negative, but in this case, the energy can't be negative because a transition is happening.
No. Here energy we are not talking about energy. We are talking about wavelength, frequency, and all that. So wavelength can be negative, frequency can be negative, energy can be negative. We discussed now in the first question. The question was, what is the ionization energy of the hydrogen atom in its fast excited state? So the energy of the electron in the fast excited state is negative, because the system is a bound system and the electron is getting attracted. So in order to make the electron free, we need to make the energy of the electron 0. So if you want to make the energy from minus 3.4 to 0, we need to supply plus 3.4 energy, and that plus 3 point energy is called as the ionization energy. So energy can be negative, but the wavelength and the frequency correspond to that energy can be negative. So it depends upon what type of transition you are seeing, whether it is transition corresponding to emission of the spectral line or transition corresponding to absorption of the spectral line. That's why the expression will change corresponding to the spectra. So here if we calculate, it will be 1 by lambda equals to R 1 by 2 square minus 1 by 4 square. R is given to us, it is 1.097 into 10 to the power 7. It will be 16, 4 minus 1. It will be 16. So lambda will be 16 by 3 into 1 by 1.097 into 10 to the power minus 7. So if you calculate, so in order to convert it into nanometer, we can say 16 by 3 into 1 by 1.097. Suppose I will write here nanometer. So this is in meter. So if I want to write in nanometer, then what will be present here, or what I need to write here?
We have to divide by 100.
Sorry.
We have to divide by 100.
No, I am just asking. I need to write it 16 by 3 into 1 by 1.097 into dash and then nanometer. Then what exactly I need to write it here?
Sir, into 10 की power 2.
Exactly. We need to write here into 100. Then I can write it in nanometer. So because 1 meter is 10 to the power 9 or minus 9 nanometer. Yes.
Sir, minus 9.
नहीं 1 meter is 10 to the power minus 9 nanometer or plus 9 nanometer.
Sir, 1 meter equal to 10 plus 9 nanometer. 1 meter
Exactly.
equal to plus 9 nanometer.
Exactly. That's why I asked this question. It is plus 9 nanometer. So in order to make it minus 9, you have to multiply 100 and then divide it by 100. So when you divide by 100, it will be nanometer, and then multiply by 100 will be coming here. So if you calculate it, it will give you 486 nanometers. So the correct answer is 486 nanometer, and the correct option is option B. So I hope this is clear to everyone. Yes.
Please once again explain why the energy can be negative.
So you see, when there is a force of attraction, then you see there are two charges. So now so in case of 1 minute, I lost. So here you see this was the postulate of Bohr's model. So here Bohr said that the electron is revolving around the nucleus in certain circular orbits, where the force required for circular motion is getting balanced by the force of attraction. Now if you talk about the potential energy between the two systems, so you know potential energy is 1 by 4 pi epsilon 0 q1 q2 by r. So here one is negatively charged, another is positively charged. So when you multiply negative with positive, it will give you negative, and the corresponding value of energy will be negative because there is a attractive force. So when the force is attractive nature, the total energy of that system will be negative. When the force is positive, then the total force, the total energy, when the total energy is positive, the nature of the force is repulsive. That's why the similar charges attract each other and similar charges repel each other, and dissimilar charges like positive and negative charge attract each other. And if you are talking about the ionization energy, for ionization energy, we need to make the electron free. The electron is free means no force is getting applied on that electron, and we know the value of energy, or the expression for what is the expression for energy. If you talk about the force,
Sir, F is equal, sir, F dot D is equal to work done.
exactly. So energy is force into displacement or distance. So when the force is attractive or negative, then the energy will be negative, and the force when the force is positive, the energy will be positive. So the repulsive force corresponds to positive energy and attractive force corresponds to negative energy. And if you want to make the electron free, then you need to make the electron so you need to get the electron transited from one position to another position where there will be no force. No force means no energy, that is the energy is zero. So here we return zero as the energy of the electron which is at a distance r equal to infinity from the nucleus. So 0 minus of minus 3.4, it gave plus 3.4. Is that clear?
Sir, then the energy of the nucleus will also be negative, sir. In that case, also in this from this formula, the energy of nucleus will be also negative, sir.
No, there is not the energy of nucleus or energy of electron. This is the energy of the system. Between we are talking about the energy of hydrogen atom or the energy of the electron present in that atom. So since that electron is getting attracted by the nucleus, the energy is negative. So in order to free the electron, we need to supply external energy to make the energy zero. So we need to supply the positive energy, that is plus 3.4, so that the ionized energy is 3.4.
Okay, sir, I understand, sir.
Then,
This I understood. Shall I ask for just
sorry, your voice is not clear. Your voice is too low.
here now I'm clear about it. But I have one general doubt. Let me clear it at the end of the session, sir.
So, no, you can ask if it is related to the course. You can ask me right now. It's okay.
Sir, we are informing that the electron is having two spins, isn't it, sir? Positive half and negative half. In this
Yes.
case, how all the energy of the electrons will be same in the energy states, sir? So
No,
if
actually,
if
see.
the first
So
orbit is going to be the energy level, and the two electrons will be having different energy states, isn't it, sir? Then how we are considering that all the electrons are behaving same when we work for the subjects, sir? So could you
okay, so
understand what I'm
no,
asking, sir?
exactly, I can understand. So as you proceed in the course, your doubts will be getting cleared. So basically, what happens
Okay, sir.
if you talk about the energy that I mentioned here? As long as the electron is revolving in a particular energy state, the energy of the electron will be constant. And here
Okay, sir.
the so we discussed here. So what was the expression of energy? Why we are writing here En? Because n is the only dependent variable for hydrogen atom. So it is mz square e fourth divided by n square h square epsilon 0 square minus 1 by 8. So here you see the expression for energy depends upon the value of n, and n is here a quantum number. We know, you know about quantum numbers.
Yes, sir.
Yes, sir.
Principal quantum, right?
Exactly. So quantum numbers are the identity of the nucleus. So here till now we have discussed about only one quantum number, that is n, which is called as principal quantum number. However, as we move forward in this course, there will be other quantum numbers like azimuthal quantum number, spin quantum number, and for spin quantum number there will be orbital spin quantum number, and there will be one is orbital motion, another is spinning motion. So one will be orbital quantum number, another will be spin quantum number. However, we will see in the future lectures, you will see the energy of the energy of the electron, as long as it is revolving in an atom or inside an atom in any energy level, the value of energy is only dependent upon the value of n. So whether it is present at n equal to 1 and n equal to 2, suppose the value of n is changing, only then the value of energy will change. Whether it is the spin is plus half or minus half, the energy remains the same. That's why all the electrons revolving in a particular energy level has the same energy. So I think in the upcoming week, like week 2 or week 3 or week 4, your doubts will be cleared, because when summer field, so basically here only, since we are talking about n equals to 1, when, so here we are talking about only one quantum number, that is n. However, just I mentioned at the beginning of the today's session, there will be Sommerfeld's model which will modify the Bohr's model, and it will say that the orbits of the electrons are not always circle, there are elliptical orbits. So when we are talking about elliptical orbits, you know there are, so for circle there is only one value of radius, that is r. However, but for ellipse there are two axes, one is major axis and minor axis. So there are another unknown, we are adding a and b. So corresponding to that there will be another quantum number. So as long as we are exploring different properties of the nucleus, each quantum number will explain a particular property. So till now we have only discussed about the energy, and energy of the electron depends only upon the principal quantum number. So as long as we, as we proceed in the course, your doubts will be getting cleared, and I think after 2 or 3 weeks more you will be able to clarify why we are taking that, or what or why we are saying that all electrons, as long as they are moving in the same energy level, they have same energy, whether they are plus or minus. Is it clear?
Okay, sir. Thank you. Okay, sir. Thank you, sir.
Okay. So now we'll move to question number 5. Question number 5 says, if K is the kinetic energy and U is the potential energy of an electron revolving around the nucleus of hydrogen atom, then what will be the relationship between K and U? Option A, K is minus U by 2, K equals to U by 2, C, K equals to minus U, and D, K equals to minus 2U. So these are
Option
the,
A.
Sir, second.
Option.
yes, one by one, yes.
Sir, option A.
Sir,
Option.
sir,
Yes.
option second, because kinetic energy can't be negative. It will be always positive.
But how can you say here kinetic energy is positive, or whether K is equals to minus U by 2 or K equals to plus U by 2? It will depend upon what is the sign of U also. It will be not depending upon K, because K is again depending upon potential energy. So if so you said kinetic energy can be negative, that is fine. So K is always positive, but the potential energy U, it can be negative or positive. It can be negative or positive. So here we can't exactly say K equals to U by 2 will be the correct option, and K equal to minus U by 2 will not be the correct option. So you need to first calculate, and then we can come at a conclusion. So can anyone tell me what will be the expression for kinetic energy K?
So
When an
kinetic
electron,
energy is Z E square by 2R, whereas potential energy is minus Z E square by R.
1 minute. How did you calculate? But so this
Sir,
is kinetic energy. Yes, this is kinetic energy K. Yes. So what
sir,
will
we know the Coulombic force, so we'll just integrate it with respect to the radius, and we'll get the potential energy that we have. And then, sir, we can use the earlier the Bohr postulate to calculate half mv square, which will be equal to Z E square by 2R.
exactly? So in order to calculate the value of half mv square, we don't need to do all these integrations and all, because we know from Bohr's postulate mv square by r equals to k z square by r square, is not it? So if you see here in the, here I have written m v square by r equals to k z square by r square. Can you see this expression? Yes, anyone?
Yes, sir.
Yes,
So
sir.
from
I can.
here only we can directly calculate. We know the expression for kinetic energy is half mv square. So here we can directly calculate what will be the value of half mv square. And if you calculate the value of half mv square, what will be the expression? Yes. So half mv square equals to, so one r will get cancelled out from each side. So it will be half K Z square by R. Is not it? We know K is 1 by 4 pi epsilon 0. So it will be 1 by 8 pi epsilon 0 Z square by R. Is this clear to everyone? So K
Yes,
is
sir.
1 by 8 pi epsilon 0 Z square by R. Now if you talk about the potential energy, so what will be the value of potential energy?
1 by 4 pi epsilon naught Z E square by R.
So it will be negative 1 minus 1 by 4 pi epsilon 0 Z square by R. So since we are talking about the potential, so here the potential energy is coming from the Coulombic force of interaction. And since the force is attractive, if you take the integration, it will be, so F you just tell na F dot dr.
It,
If you, yes,
sir, it will be minus from minus infinity to R. So 1 upon minus infinity will become 0 and only R will remain.
exactly. So it will be minus 1 by 4 pi epsilon 0 Z square by R, because since the force is attractive in nature, energy will be negative, and that energy is the potential energy. So here U is minus 1 by 4 pi epsilon 0 Z square by R. So if you want to establish a relationship between U and K, you see what will be the correct. So you see it is, so U is minus 1 by 4 pi epsilon 0 Z square by R. That implies minus 1 by 8 pi epsilon 0 Z square by R into 2. So K is, sorry, 1 minute.
Sir, so we have to put an another minus to cancel the minus of potential energy.
Exactly.
Okay, sir. Now I understand. I think I has.
So sorry, here, here this is, so here not K, it will be U. So U equals to minus, sorry, this part 1 by 8 epsilon 0 Z square by R, this is K, so it is minus K into 2. So U is equals to minus 2K, or K equals to minus U by 2. Is this clear to everyone?
Now, yes, sir. Now it is clear. I have a small confusion. Matlab,
Yes.
in that option, I had small confusion that energy means kinetic energy. I heard, I read somewhere that kinetic energy can't be negative, so I got confused. But now I understood that minus sign here is for canceling the minus sign of potential energy.
The minus sign, the minus sign is present here because the potential energy is negative. That's why, mm, since kinetic energy can't be negative, we have to add a minus, that then only the energy will be positive, because the potential energy of the electron when it is present inside the atom is negative. Okay, so we will move to the question number 6. The question number 6 says, so is this clear? The previous question is clear to everyone?
Yes, sir.
Yes, sir.
K is equals to minus U by 2. Okay, so we'll move to question number 6. Question number 6 says a black body radiates heat at the rate of 5 calorie per centimeter square per second when its temperature is 27 degrees Celsius. The temperature of another black body is 627 degrees Celsius. What will be the rate of heat radiation from it? Options are: option A 116 calorie per centimeter square per second, 405 calorie per centimeter square per second, 5 calorie per centimeter square per second, or 45 calorie per centimeter square per second.
Sir, option B.
So the question says a black body radiates heat at the rate of 5 calorie per centimeter square per second when the temperature is 27 degrees Celsius, the temperature of another black body is 627 degrees Celsius, then what will be the rate of heat radiation from it? So here one here there are two different temperatures, and correspond to that temperature there will be two different rate of heat radiations. So can anyone tell me what will be what is the law that governs the rate of heat radiated from a body at a particular temperature?
So
Sir,
Stefan's
it is
Boltzmann
Stephen's
law.
law.
Yes. So what it says?
Sir, E is equal to sigma T raised to 4, and the sigma is 2.89 into
No,
10 to power.
no. So here I am discussing about the physical things. So I am not going about the numerical or the expression. What is the basically what Stefan's law says?
Sir, it says that when temperature of any a black body increases, then it emits the energy, and this is directly proportional to T raised to 4 of that body.
Exactly. So according to Stefan's law, the total energy radiated by a body per unit time or per unit time and per unit area is directly proportional to the fourth order of the temperature of that body. So if you are talking about the two temperatures, one is 27 degrees Celsius, another is 627 degrees Celsius. So for a black body, we can write for a black body, if we talk about E will be sigma T to the power 4. So what is the value of sigma? Because although we don't here need the value of sigma, because there are two temperatures, and when we take the ratio, it will be getting cancelled out. But can anyone tell me what is the value of sigma? That is the Stefan's constant. So what is
Sir,
this?
2.89.
Yes, once again.
Sir, 2.89.
Not 2.89. Stefan's constant value is 5.67 into 10 to the power minus 8. 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. And here this E is heat radiated per unit area. That is the rate of heat radiation. That is watt. So this is joule per second per meter square, which is watt per meter square. So now is this clear? This is the expression for Stefan's law. So the heat radiated is directly proportional to T to the power 4. So now if we are talking about the heat radiations at two different temperatures, so E1 by E2 will be T1 to the power 4 by T2 to the power 4. So here E1 is given to us. E1 is 5 calorie centimeter minus 2 second minus 1. So here you can see, here it is given in 5 calorie per centimeter square per second, and here also all the options are in same unit. So we don't need to convert to any other unit. So we will directly write. So U1 is 5 calorie per centimeter square per second, and T1 is how much?
Sir, 300 Kelvin.
Exactly. So it is, so all these temperatures at absolute temperatures of the body. So we need to convert it from degree centigrade to Kelvin. So it is 300 Kelvin then, and T2 is given to us. T2 is 627 degree Kelvin, which is
900 Kelvin.
900 Kelvin. So now if we put the expression, what will be the value of E2? E2 will be T2 to the power 4 by T1 to the power 4 into E1. So E2 will be 5 into 900 divided by 300 to the power 4. So it is 5 into 3 to the power 4, that is 5 into how much?
81. 81.
81, that is 405 calorie centimeter minus 2 second minus 1. So it is calorie per centimeter square per second per unit time per unit area. So the correct answer is 405 calorie centimeter minus 2 second minus 1. So is this clear to everyone?
Yes,
Yes,
sir.
sir.
Yes, sir.
Exactly. So also there is one physical thing that is, so we can if you talk about the Stephan's law, then we can correlate it with the black body radiation. So now since these questions are coming from the topic of black body radiation, so I think it will be better if we can discuss a few things about the black body radiation. So now if we talk about black body radiation, so can anyone tell me what is called as a black body?
Sir, it absorbs and emits the radiation at all the temperatures.
It absorbs energy of all wavelength
So a black body is a body which absorbs all the radiations
and
fall- falling on
emits
it.
the radiation with respect to temperature.
Exactly. So if you talk about, so there is a Kirchhoff's law in thermodynamics. You know, there is a law called as Kirchhoff's law in thermodynamics.
No, sir.
So according to Kirchhoff's law, at a particular temperature, the ratio of emissive power to absorption power of a body is constant, and that constant is related to the emissive power of a perfect black body at that temperature. So if you talk about a black body, since that black body absorbs all the radiations falling on it, so a black body is a perfect absorber and a perfect emitter, because according to Kirchhoff's law, a good absorber is a good emitter, because the ratio of absorption power to absorptive power or emissive power is constant. So when a body absorbs well, it will reflect well. So when you heat a body, it will first appear red. So as long as you are supplying heat, it will then become yellow and then become white. So it will start radiating. So when the thermal radiation gets emitted by the body, there will be a continuous frequency distribution. So that frequency distribution and that so corresponding to each frequency, there will be some radiation emitted. So there is a black body radiation curve that you must have uh, read in the question, or sorry, you must have read in the lectures. So there is a blackboard radiation curve. So if you talk about the variables in x and y axis, so this is frequency and this is power density or the energy density. You can take as u nu t. So since the black body radiation is a, so the black body emits continuously corresponding to all frequency, so the curve will be a continuous curve, so it will be somewhat like this. So corresponding to all frequency, you will get some radiation, and the radiation will cover so you can see here this point is not touching here because the frequency will not be zero. Since the black body is emitting some energy, so energy of the body is non-zero. So non-zero means frequency will not be zero. So always the black body curve starts from a non-zero value of frequency and energy. Is that clear to everyone? That is one of the most important thing. So now if you talk about, suppose, so we are plotting here, so this curve corresponds to a particular temperature. So for all values plotted in this curve, T is constant. Suppose this is T1, then if you are talking about the frequency, then it will be T2, T3 like that. So at different temperatures, the curve will be different. It will be like this, like this. So suppose this is T1, this is T2, this is T3. So as the temperature increases, so as you can see here, the expression says E is right proportional to T to the power 4. So basically this E, that is the total uh, the total energy radiated by a black body. So basically this E or rate, or if you can say U, so this U gives the total area under the curve. Total area under the curve. So that area will be direct proportional to T to the power 4. So as so T1 is less than T2 is less than T3. So as the temperature increases, it will emit more and more energy. That's why the area under the curve increases, and that area, and the expression of the area will depend upon the temperature at T to the power 4. This is the physical explanation of Stefan's law. Now there is another law which is called as Wien's law, and according to Wien's law, there is a particular value of wavelength or particular value of frequency corresponding to which the energy density or the rate of heat radiation is maximum, and that depends inversely upon the value of temperature. So if I talk about the Wien's law, according to Wien's law, the wavelength corresponding to maximum emissive power is inversely proportional to temperature. So lambda m is direct proportional to 1 by T, or lambda m equals to B into T, where B is Wien's constant, and it is 2898 into 10 to the power minus 6 meter per Kelvin. So someone is saying na 2.89, 2.89.
Territory B upon T.
Sorry, it is B up exactly. Sorry, it is B divided by T. So as the temperature increases, the value of lambda corresponding to maximum emissive power decreases. So if you plot a blackbody radiation curve, so suppose this is minimum, so this is the maximum value of frequency. So here we are talking about wavelength. So if you are plotting the blackbody radiation curve and you take wavelength here, so suppose this is corresponding to T is equals to 1, and this is the maximum value lambda m1. Then if T equals to 2, sorry, if we plot another T, suppose this is T2, so this is T2, so this is the maximum value of u lambda, and this will be lambda m2, this is lambda m1. So when T2 is greater than T1, lambda m2 is less than lambda m1. Is this clear? So this is Wien's law. So now if we talk about the question that we were discussing, so the question says, under identical condition, a black surface absorbs dash heat in compared to a white surface. Options are option A equal, option B negligible, option C more, and option D less.
Sir, option C.
Anyone other?
Option C.
So why
Option
option
C.
why option C? Because we know the body which is appearing black, that means it is absorbing all the radiations falling on it. That's why the black body, we are discussing, the black body absorbs all the radiations falling on it. So under identical conditions, a black surface will absorb more heat in compared to the white surface. So here the correct option will be option C, that is more. Is this clear to all?
Yes, sir.
Yes,
Okay,
sir.
so we'll move to question number 8. So the question says, radiation with maximum energy is X-ray, UV ray, visible ray, and infrared rays. So if you talk about, so all these rays correspond to electromagnetic spectrum. So if we talk about electromagnetic spectrum, so these corresponds to the electromagnetic spectrum.
Sir, option A.
Magnetic spectrum. So if we talk about the, suppose this is lambda, suppose 1 minute. So suppose this is so it can be either lambda or frequency or wavelength or frequency. Suppose we are talking about lambda. So here lambda, so lambda is so lambda is, so here lambda is minimum, here lambda is maximum. So the part of the spectrum having maximum value of lambda is called as which wave? So it is radio wave, then there will be microwave, then there will be infrared,
Infrared,
then
visible
visible,
spectra,
then UV,
ultraviolet,
then X-ray,
X-ray, gamma
then
ray.
gamma ray. So you can see here, and we know E is inversely proportional to lambda because E is equals to SC by lambda. So lambda minimum means energy is maximum. So the radiation with maximum energy is which one? Here the options are ultraviolet, visible, infrared, X-ray. So
X-rays.
infrared, visible, UV, X-ray. So there are 4 here. So X-ray has the maximum energy and infrared has the maximum wavelength. So if you draw it, suppose this is frequency axis and frequency is increasing this way, then so lambda is increasing in this way and frequency increases this way. So first will be infrared, then it will be visible, then it will be ultraviolet, and then it will be X-ray. So maximum frequency, this side is maximum wavelength. So the part of the spectrum having maximum frequency is X-ray, or maximum energy is X-ray. So the correct option is option A. So does anyone know how the X-rays are produced?
Yes, sir.
Yes. So can you say? Can you just
Sir,
explain a bit?
sir, through thermionic waves or through electromagnetic wave, or by
No.
excitation through electron or a photon.
Exactly. So uh, since we are talking about X-rays and X-rays have higher energy, so the electron that is involved in these transitions are the X-rays which correspond to the transition of the electrons, whether those electrons are innermost electron of the atom or outermost electrons of that atom.
Sir, outermost.
Sorry, is it?
Outermost.
No, it will be innermost electrons because innermost electrons have minimum energy
They,
and
they,
yes,
they are very closer to nucleus and it needs excess energy to come
exactly.
out.
So exactly. So since the electrons that are present closer to the nucleus have more energy, means more negative energy, we need higher and higher energy to remove that electron, and when that electron will get removed, it will be having maximum energy, so it will emit the radiation at higher frequency, and that is called as X-ray. So X-rays have lower, so X-rays are having lower wavelengths but higher frequency. So basically, generally what happens, so there are, so if you need to see a spectra of X-ray spectra of one particular surface, so there is a target surface here. So this is target and this is the source. So electrons will move from here to here. Suppose this is target, it is, suppose it is molybdenum or any other thorium or a molybdenum like that. So we want electron to move from this electrode to this electrode. So we need to bias bias this electron negatively and bias this electrode positively, and we need to apply very high energy, because then the electron will be getting accelerated over such a high potential, like 10 kilovolt we can say. So when we apply 10 kilovolt, so that energy the electron will absorb, or electron will get accelerated in a potential difference of 10 volt, 10 kilovolt, and then when the electron get hit on this target, then they will supply their excess energy to the atom, and that excess energy will be and that excess energy will be absorbed by the electron, and it will get excited from one orbit to another orbit, or the from innermost orbit to higher orbit. And then, since the lifetime of higher orbits are not zero, so the lifetimes of higher orbits are not infinity, after some time they will again come back to the initial orbit, and then while coming back to the initial orbit they will emit the radiation that will correspond to the difference between the two orbits. And if you are talking about, so we discussed now the X-ray that is getting emitted, so X-ray is getting emitted, so emitted means the transition is occurring from n equals to, suppose it is n equal to 3 to n equal to 2, is not it? Then the because the energy difference between uh, 10 point, so the maximum energy difference is 10.2, then the energy difference goes on decreasing. So in order to have, so the electron, in order to have more energy, the transition need to be corresponding to the uh, minimum values of n, that is uh, the innermost electrons. For example, n equal to 2 to n equal to 1, the transition that will occur, the energy emitted will correspond to the X-ray. That's why the transitions involved in the X-rays production are transitions of the innermost electrons. So we can discuss. So now the time is, so we are getting late. We need to discuss a few more questions. So at the beginning of next interaction session, we will discuss more briefly about how the X-rays are produced, how the spectra look like. So there are basically two types of spectra. One is another one is characteristics X-ray spectra. Another is background X-ray spectra. So all these things we will discuss in the next interaction session. So now we'll move to question number 9. According to Wien's displacement law, where lambda m stands for the wavelength at which the intensity of the radiation is maximum, and T is the absolute temperature of the body, then which is the correct option? Option A, it is proportional to root T, inversely proportional to T, inversely proportional to root T, or inversely proportional to T square. We have already discussed it. So what will be the correct option? So this is Wien's law, Wien's displacement law.
Sir, option B.
Yes, so the correct option will be option B. So we have already discussed it. Here we are discussing na. This was the Wien's displacement law. Is this clear to everyone?
Yes, sir.
Okay, so we will move to the next question. The question says, the sun gives maximum emission at the wavelength of 5,500 Armstrong. Estimate the temperature of the sun considering that the sun is a black body. Given Wien's displacement constant is 3 into 10 to the power minus 3 meter into Kelvin. So these are the four options. Option A, 5,500 Kelvin. Option B, 55 into 10 to the power 4 Kelvin. Option C, 5454.5 Kelvin, and option D, 15,000 Kelvin.
Sir, option C.
So how you calculated it?
Sir, I have solved this question last time also. So like multiply the
Last
lambda
time
m
means,
by.
sorry.
Sir, in the Saturday like live
Okay,
interaction,
okay. Yes.
this question was repeated.
Okay, so since you have already attended the Saturday question, so first let other students to solve the questions, and then uh, you need to tell the answer. But when I am just ending the question, I am reciting the question, and I am just stopping, and then you are saying this is the correct answer. So let others also solve this question, and then we will discuss what will be the correct answer. Is this clear?
Yes, sir.
Okay. So I would like everyone to solve this question, and in the next interaction session, we will discuss the solution of this question, and we'll discuss a few things related to the excess production or excess spectra, and then we'll solve more problems that will be based on the week 3 lectures. So I hope this is clear to everyone.
Yes, sir.
Okay, so is there any doubt related to the questions that we solved in today's session?
No, sir.
Okay, so Thanks for joining today's international session. We will discuss a few more problems in the next week. That's it from my side.
Sir,
Thank you, sir.
I
Thank
have
you, sir.
one doubt.
Yes.
Sir, while solving the assignment, I
Yes.
came across a particular problem. Uh,
Yes.
Let me suggest. Yeah. So question number 10 for the week 2. So, sir, like it was which of the following statement is true regarding Bohr's model of hydrogen atom? Sir, I gave my answer by just discarding the false one, but the truth statement must be energy of the electron bound to nucleus increases as it shifts to outer orbits. So,
Exactly.
sir, I said didn't fully understand what the statement was trying to tell. Was sir like when we were deriving the formula, we came to like E is inversely proportional to n square.
Exactly.
So, and here the statement is coming true. So I was yes.
Because the energy is negative. Energy. So so minus 13.6 and minus 3.4. So which is higher, minus 13.6 or minus 3.4?
Minus 3.4.
Exactly.
Okay,
So
sir. So
minus
negative.
so minus 13.6 corresponds to n equal to 1. It corresponds to n equal to 2. So as the electron moves higher and higher, the energy of the electrons becomes lower and lower. That's why higher the energy level of the electron, lower will be the energy required to ionize that atom. Is this clear?
Okay, sir.
Okay. So here the energy is negative. That's why I gave more emphasis on the problems 1 and 2 we were explaining. So why it is negative, why it is not positive. So since it is a bound system, energy is negative, and the lowest energy state is always the ground state. So as long as the particle is in ground state, it is in the most stable state because the energy is minimum. So in order to make the electron come out of that ground state, we need to supply the maximum amount of energy. So the maximum energy, so the ionization energy of the hydrogen, if it is present in the ground state, is 13.6 electron volt. But if it is present in the fast excited state, it will be only 3.4 electron volt. So as long as the electron is closer to the nucleus, higher will be the amount of energy required to ionize that atom. I hope this is clear to all. So we
Yes,
will
sir.
stop our discussion here today and we will continue our discussion in the next week. Okay. Thank
Thank you,
you
sir.
all. Good night.
Good night, sir.